So Bohr's model of the atom makes a lot more sense than Rutherford's because it can explain why we can see different colors of light come off of the atom. And that's kind of what we have right over here, where we have the positively charged nucleus. You can see the electron living right there, and it does want to tend to live in the n=1, or the ground state, the most. However, when light of just the right frequency hits it, then it can excite it, and it can live in all of these shells. And we just watched it go up to the n=5 state and then emit a photon of a different color, and then drop down, emit a photon of a different color, drop down, emit a photon of a different color, and so on and so forth. So we can illuminate this thing. Certain frequencies will excite it, and certain frequencies will come out. It will tend to mostly absorb the higher energy stuff, so it's going to absorb mostly the UV, and then it can spit out some of the lower frequencies, and we will definitely have very distinct frequencies because we have very distinct orbits. So you can kind of see that we have these distinct colors that come off of hydrogen. Now there's one teeny tiny problem with Bohr's model. First of all, it doesn't explain why these orbits have to exist, or why they only exist in these very discrete little chunks. And the other problem is if you think back to physics 242, if we have a moving electron, it has a changing electric field and a changing magnetic field, and so this moving electron should in theory be emitting electromagnetic radiation, and it should be constantly losing energy. So it's going to look a little bit more like this. Actually, I'll go ahead and make this guy a little bit slower right over here. If we were to kind of think of it, it should be spiraling inwards to the nucleus and then kaboom, and we know that that does not happen. So that's going to lead us to this idea that this electron is going to have some wave-like properties, and so now rather than having an electron, we have an electron wave. And I'm going to speed this guy up, and we can excite this wave, and this wave is only going to have constructive interference for certain patterns when this pattern has essentially 1 or 2 or 3 complete wavelengths upon it. Otherwise, the wave will essentially not fit in there, and this orbit will not be able to exist. And so this is more of a de Broglie concept. So, as I mentioned when I had the simulation up, classical physics does fail, because if in classical physics we're going to have this moving electron, and it is going to be constantly radiating light, and actually as it spirals around before it crashes into the nucleus, it's going to be constantly emitting energy, radiation, and it will crash. And actually the colors as it spirals in is going to get shorter and shorter and shorter because it's going quicker and quicker and quicker. But in fact, atoms are stable, and this does not happen. They're only going to emit light when they're excited or an electron is hopping between energy states. So along came this fella by the name of Louis de Broglie, and he said, you know what, if we can have photons, which have both wave and particle nature, then we can associate a wave with every single particle, even things like electrons. It doesn't have to just be photons. And we can say that its momentum is going to be related to its wavelength, and inversely so by using Planck's constant, which looks a whole awful lot like what we saw for photons. And he also kind of said that Bohr orbits are going to exist when and only when this wave is going to have constructive interference. It's not going to be able to live there if it has destructive interference. And so we can treat this electron kind of like a standing wave, as we saw in the simulation. So what does this kind of look like? We saw it in the simulation. We're going to have constructive interference when the wave closes upon itself, and essentially we're going to need an integral number of wavelengths fitting evenly onto the circumference of the orbit. Otherwise we're going to get this, and this looks like destructive interference, and the wave will collapse, and we cannot have a wave that exists. We can't have an electron that lives inside of this orbit. So again, the orbiting electron is going to be treated like it's a standing wave, and it will only exist when the circumference is equal to a whole number multiple of wavelengths. So we could even say 2 pi r is going to be equal to lambda times n. And again, if the wave is not in phase, it will have destructive interference, and so this right here is a bad orbit, and we will not observe any electrons there. And this leads us into the wave-particle duality for anything that has mass or matter. So this we can treat electromagnetic waves as having both wave particles and wave properties and particulate properties, and we can do the same thing for electrons. So an electron, or any chunk of matter, can have some energy that will be written as such, Planck's constant times the frequency, as well as having some momentum. So let's go ahead and take a look at, suppose we had a 2 eV electron, or better yet, maybe an electron with an energy of 2 eV. You could convince yourself that this thing is going to have a momentum. I'm going to save you the difficulty, or save you the painful process of watching me solve for it. You can convince yourself that it should have a momentum of 7.6 times 10 to the negative 23 kilograms meters per second, essentially using that energy and that frequency as well as the mass of an electron. And so we could say that the wavelength of such an electron is going to be equal to Planck's constant divided by the momentum, which is going to work itself out to be 0.87 nanometers. And if you think about it, this is much less than visible light, and so we can resolve things using electron waves that we cannot resolve using visible light, and that's why we use things like electron microscopes. Now, how come we don't observe the wave-like nature of ordinary everyday objects? If we were to think of just having a tennis ball traveling at 100 miles per hour, then the momentum is going to work itself out to be 2.7 kilograms meters per second, just the mass times the velocity. And that tells us de Broglie's wavelength is going to be h divided by the momentum. And so 6.626 times 10 to the minus 34th divided by 2.7 is going to be 2.45 times 10 to the minus 34 kilograms meters per second. And as you can see, this wavelength is really tiny, so we're never going to observe the wave-like property of, like, your pen or something like that. The wavelength is just too small. So I do want to come back to the quantized energy levels very briefly. You could convince yourself that if you were to recognize that you need to have integral multiples of wavelength on your circumference, you could kind of take your atom right over here and say that you're going to have waves and kind of unwrap them. Then you're going to see n is equal to 1 is just going to have one wavelength. N is equal to 2 is going to have two wavelengths, n equal to 3 is going to have three wavelengths, and so on and so forth. And something else you could kind of be able to visualize is the spacing between these is going to get closer and closer and closer and closer, which is going to behave exactly as we would expect to based on the spectrum of hydrogen. So again, this model of electron waves explains why we don't have that kaboom in the simulation where the atom shrinks upon itself. It's because we're treating these electrons now as waves. And again, it also explains that why we have to have discrete orbits and also discrete energies and discrete wavelengths that come out of, say, a hydrogen atom. So if de Broglie waves do exist and we can treat electrons as having wave characteristics, then electrons should be able to undergo diffraction, and they should be able to interfere just like photons do. And it turns out that this does happen. And if we were to take a look at the diffraction pattern from a circular aperture using both X-rays as well as electrons, you can kind of see that here's the aperture down here, and you can see the diffraction rings kind of coming around it. And kind of one difference between the X-ray diffraction and the electron diffraction is the wavelength of electrons is much smaller, and so you tend to get a much clearer picture. This is essentially why we use electron microscopes to look at image or to create very detailed images, it has to do with the fact that the wavelength of an electron is very small, and we can get very fine detail of things like this mosquito right here. And just a quick look at a electron microscope. If we had a high voltage power supply with a cathode where we're going to start getting some electrons boiling off of it, then we can accelerate it through a voltage and have, kind of a lens, a magnet to kind of control this guy. You put a specimen right in there, and we have a few more lenses right over here, and we can create an image where there's going to be constructive and destructive interference now of the electrons, again using the wave-like property of electrons to form an image.